Hello everybody, and welcome to Honors Global Climate Change. My name is Mr. Muick, and I'm going to be your instructor for this course. A couple things that I'd like you to know is that these videos do not constitute the whole course. They are just the direct instruction component. Attendance of our live sessions is vital for you to get all the information. So come on along, and we're going to learn a lot in this incredible journey together. Okay, so every day when you come into this class, you're going to see an agenda slide, and you're going to have this in your note sheet as well. So when you go on the Google Classroom page, you're going to find that this document is linked for you as well. And in it, you're going to see what the objective is. So for example, today, we're going to become familiar with the outline of the course and then be able to explain what climate change is. There's going to be an agenda, and there's going to be some homework. So if you're going to look, you're going to see that today you do have a couple pieces of homework. One is you're going to sign up for a current event day. I'll explain that in a little bit. And two, you're going to submit a photo of your notes from today to Google Classroom, and that will kind of serve as your attendance for the class. The other thing I want you to notice is that in this document, there are links to a lot of things. And when you are going through, feel free to pause the video and click on the links so you can learn more about stuff. So for example, our first link is going to be about this image. And so every day you're going to see a picture and a quote from a person that I think is relevant to the course content. And so let's go and we'll try it out. Oh, this link is taking us to a YouTube video. Let's watch.
But why, some say, the moon? Why choose this as our goal? And they may well ask, why climb the highest mountain? We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
In the 8th year of manned flight into space, the National Aeronautics and Space Administration prepared men and equipment for the most advanced manned mission to date.
Apollo 8 was the first flight to the moon. We had information that the Russians were going to put a man around the moon in the late fall of 1968. Consequently, we changed Apollo 8's mission to fly to the moon, orbit the moon, and come back, and we did that over the Christmas holidays. We had to build a Apollo spacecraft that would hold 3 people. We sat on top of a large rocket called the Saturn V. It was a 3-stage vehicle that gave us enough velocity and on the proper course to coast all the way to the moon.
The engines are on. 4, 3, 2, 1, 0. We have liftoff.
Man, perhaps on the way to the moon. All continues to go well.
My 2 companions were Frank Borman and Bill Andrews. That was the 3 of us that made the flight.
You can still hear you, Apollo 8? Yeah, we hear you loud and clear, Apollo 8. Okay, your first stage was very smooth, and this one is smoother. This is smoother and smoother. Looks good here.
The flight took about 3 days to get to the moon. We had charts of the various craters that we wanted to see. We wanted to look at the flat areas for making landings and later flights.
Houston, what does the old moon look like from 60 miles, over? Okay, Houston, the moon is essentially gray. No color.
We didn't know the significance of the mission with regards to things that we did or things that we said until we got back home. It was the 4th orbit when we finally came to a position where we saw the Earth.
Oh, yeah, look at that picture over there. There's the Earth coming up. Wow, that's great. Got a color film, Jim?
And then Andrews asked me for colored film.
And they roll a color film. Oh, yeah, that's color blue. Quick. Yeah, I got it right here. That's pretty good. I got it pretty clear right here.
And Anders does take, I guess, several pictures. When I say 250 at F11.
Oh, I got it. Oh, that's a beautiful shot.
And as Anders takes the pictures, one of them, as we learn after we get back home, became the very famous one.
Following a direct descent flight path, Apollo 8 traveled 1,560 miles across the Earth's surface and splashed down in the Pacific with pinpoint accuracy.
When we landed, of course, we were well received, being the first flight around the moon and very successful in getting back. But the country in 1968 was sort of in a turmoil. Martin Luther King and Bobby Kennedy both were assassinated. We had a war going on. It was one after the other of bad news, either in Vietnam or in the continental United States. And then the launch of Apollo 8 brought a binding to the people of our country. It was a very significant factor in how people felt about themselves and their environment. The Earthrise photo in just one picture gives the person a complete understanding and glimpse of his or her position in the universe by looking back at the body that she calls home. It was the first time that people actually knew what the Earth looked like and where they were living.
Okay, so I shared that video with you for two reasons. The first reason I shared that video with you is because I think it's a really good example of what we can do together when we put our minds to something and we put the resources behind it and we make it happen. The other reason I wanted to share this with you is because this picture, this photograph, was really the start of a modern movement, many people to come together to look at how we impact our Earth and what we can do about it. And so those two things, us having the launch of the modern environmental movement combined with an example of us coming together to do something spectacular, I think is a really good place to frame ourselves at the start of this journey together. So come on along. We're going to talk a little bit about the structure of the class, and then we'll get into a little bit about climate change. This course was produced in collaboration with the University of Michigan and Dr. Ricky Rood from the School of Engineering. And so last year, Mr. Payson, Mrs. Payson, and myself met with Dr. Rood weekly in order to put this together, and we think that together we have created something that should be a really excellent opportunity and powerful for you. I do not want this class to be just another box check on your schedule. I really want you to use this as an opportunity to learn about the world around you and how you fit into it and what you want to do. The other thing that this course is based on is the IPCC Report. And the Intergovernmental Panel on Climate Change was put together by the United Nations to bring together all of our knowledge of climate change and report out on it. And this is the largest collection of, or the largest, most thorough report ever produced by the scientific community. And we're not going to read it all because it's over 5,000 pages, but we will use the synthesis report, which is a summary of the report's findings in our class. So, this course is broken up into 3 units, and the 3 units are going to loosely follow observed changes in their causes. So what is climate change? What's happening? Second one, we're going to look at future climate changes, risks and impacts. And then finally, we're going to look at what we can do about it. Now, because this problem is so interconnected, we're not going to be able to look at these things in isolation. And so the whole course is going to be cyclical in nature, where we're constantly going to be going and looking at, okay, so how does this impact what can we do? How does this impact what's going to happen in the future? Again, how do we know exactly what's going on? because the problem is complicated. We will not have a textbook per se, but we are going to use the research from the IPCC, which you will read the summary report, and then we're going to read a couple of journal articles that have been published throughout time. And all of these articles have been picked because members of the IPCC have stated that they believe that these are the most influential articles ever written on the topic. The course is a one-semester class, and it was originally made for 42 80-minute class periods, although some things have changed because of COVID. So instead of having one class period, you're going to have a video and then a virtual session together. So if we're looking at this, our first test is going to be about 13 class periods in. So you are going to have 3 ongoing projects this semester. 2 of them are going to be with a group, and 1 of them is going to be on your own. The 2 with a group are going to be a journal club and a semester project, and then on your own, you're going to do a current event. Now, I will demo these for you before it's your turn, so you know what you're going to be doing. Most advanced courses at the university level have a journal club associated with them. And this being an advanced course at the Math and Science Center, we are going to be no different. And every couple of weeks, we're going to get together in our virtual class time, and we are going to discuss an article. And so the first time we do it, we're going to get together, and we're going to read about the artificial production of carbon dioxide and its influence on temperature. And I'm going to lead this discussion. So you're all going to read it ahead of time, and then we'll talk about it in class. Your project is going to be you and a group of your friends are going to sign up for leading other review sessions, and so you will then facilitate those discussions. You will also have a semester project. Now, I'm going to leave this semester project semi-open-ended for you because I want you to do something that you find value in. If you find yourself doing something for your semester project that you don't think is worthwhile, talk to me and we will find something else for you to do. I'll give you a couple examples, but you can take it elsewhere if you want. If you want to do something different, just come talk to me. So one of the ideas that you can do is you can create a climate assessment for a location. You can't do Grand Rapids because that's the example. And what you would do is you would write down and do research, and you would describe for the city of Grand Rapids what the climate is like there, what's occurring in Grand Rapids, how it's going to change, and what Grand Rapids should do about it. So that's kind of an exhaustive thing. And I'm going to expect that you get it to a point where at the end of the semester, you could send this document to your destination if you so choose. So that's kind of the standard that we're looking at. You're trying to create something where you could take your final product and actually deliver it to somebody for practical use. And you don't have to do a city. If you want to look at a state park, you could do that. If you want to do a different type of research project, that's okay too. Just make sure you approve it with me. And then finally, our current events. So because climate change is ongoing and there's constantly news about it, we're going to do current events. I'll do the first one, but every day somebody's going to have a turn at sharing an article that they find. And you can have an article from a scientific source like NASA or a popular source like CNN. It's up to you, but sign up in the document on Google Classroom and sign up for which type, a popular source or a scientific that you would like. Now, if you notice these are links, do not feel that that means you have to get your current event from Scientific American. If you have a different location that you would like to get your event from, that's fine as well. So with that, we have now kind of given you a background on the course, and so let's get into the problem just a little bit. So right now, you are looking at a graph showing the annual ocean heat content compared to an average. And I'm starting off with this because a lot of times we hear about temperature and climate change, and temperature is not the most important factor. The most important factor in climate is Earth's energy budget and how much energy do we have. Because temperature isn't the only way we see climate change manifests itself. We also see it in stronger winds and hurricanes. That's a factor related to energy, not related to temperature. So, if we look at this graph, we can see that if we're comparing the annual amount of, or the ocean heat content, so this is how much energy there is in the ocean, and comparing it to a baseline, which is 1993, you're going to see some values here, which we're going to call an anomaly. So this is not saying that in 2010 we had 90 times 10 to the 21st joules of energy in the ocean. We're saying in 2010 we had 90 times 10 to the 21st joules of energy more than we did in 1993. And a lot of our values are going to be reported in anomalies from some baseline. And we can see that over time, both our surface water and our deep water have increased in heat content. And that's regardless of the data set that's used. There's a little bit of variation if you collect your data points from different places, with different methodologies, you get slightly different answers, but overall, you see the same trend. We see the surface is heated up more than the depths, which makes sense because the surface is closer to where we're receiving all of our energy. It takes time for that energy to work its way down. And we'll see it continue to go on. Now, well, here we go. I've accessed another link by accident. I'm sorry. Didn't mean to do that. I just meant to go to the next slide. That's a good example of how a lot of these are actually linked to their original location. If we look here at this graph, which I got from Dr. Rude, it was originally produced by NOAA, we can look at temperature, something that you are probably more familiar with. And here we can see the deviation or the anomaly in temperature from the 20th century average. And so if we look at, let's see, 1900, it was colder than the average temperature for the century. And this is true on land. So if we look at the land surface temperature, we're taking a measurement of temperature 2 meters above the surface. So this is in the air. This is true in the ocean. And when we look at ocean surface temperatures, we're not actually measuring the temperature of the water. We're measuring the temperature of the air 2 meters above it, and the global average for land and ocean. And regardless, we can see that our temperatures over the last century have increased. How much? Almost 2 degrees Fahrenheit. So, let's take a look at a decadal perspective. And I don't have 2010 to 2020 on here quite yet because that's not released. But we can see that 2000 to 2010, the decade was warmer than the decade from 1990 to 2000, which was warmer than the decade from 1980 to 1990, which was warmer than the decade from 1970 to 1980. And you'll see that that trend continues for this new decade once this data is finalized. And the difference between these is actually increasing. What does that mean? It means that Earth is heating up, and that heating up is accelerating. That's temperature. What causes it? Well, an increase in temperature is caused by an increase in carbon dioxide, amongst other things. And we can look at the concentration of carbon dioxide in the atmosphere and how that has changed over time. So, starting in the 1950s, carbon dioxide concentrations in the atmosphere were measured in Hawaii, and you will read this article from Keeling in your journal club, so we won't talk about it too much, but what was found right now that we can talk about is that the concentration of carbon dioxide in the atmosphere goes up and down and up and down and up and down, but even though it's going up and down, up and down, up and down every year, over time, it is increasing. So even though it might be lower at one month than the previous month, over the course of year to year, it's going up. And if we go to the present day in 2020, we're going to find our atmospheric concentration at about 410 parts per million. Why does it go up and down? Well, it's the Earth's breath. Every year in the summer, plants conduct photosynthesis. They take in carbon dioxide. They're storing it inside themselves as sugar. And when that happens, the concentration of carbon dioxide in the atmosphere drops. When winter occurs, carbon dioxide gets released back into the atmosphere through respiration and decomposition, and it goes back up. And every time we're doing this, we're finding that every year, every time it goes up, it's getting higher. We can take a look at the changes in concentration of carbon dioxide within 1 year in this simulation.
Hi, this is Bill Putman. I'm a climate scientist at NASA's Goddard Space Flight Center. What you're looking at is a supercomputer model of carbon dioxide levels in the Earth's atmosphere. The visualization compresses 1 year of data into a few minutes. Carbon dioxide is the most important greenhouse gas affected by human activity. About half of the carbon dioxide emitted from fossil fuel combustion remains in the atmosphere, while the other half is absorbed by natural land and ocean reservoirs. In the northern hemisphere, we see the highest concentrations are focused around major emission sources over North America, Europe, and Asia. Notice how the gas doesn't stay in one place. The dispersion of carbon dioxide is controlled by the large-scale weather patterns within the global circulation. During spring and summer in the northern hemisphere, plants absorb a substantial amount of carbon dioxide through photosynthesis, thus removing some of the gas from the atmosphere. We see this change in the model as the red and purple colors start to fade. Meanwhile, in the southern hemisphere, we see the release of another pollutant, carbon monoxide. This is a gas that's both harmful to the environment and to humans. During the summer months, plumes of carbon monoxide stream from fires in Africa, South America, and Australia, contributing to high concentrations in the atmosphere. Notice how these emissions are also transported by winds to other parts of the world. As summer transitions to fall and plant photosynthesis decreases, carbon dioxide begins to accumulate in the atmosphere. Although this change is expected, we're seeing higher concentrations of carbon dioxide accumulate in the atmosphere each year. This is contributing to the long-term trend of rising global temperatures. The Orbiting Carbon Observatory 2, or OCO2, will be the first NASA satellite mission to provide a global view of carbon dioxide. OCO2 observations and atmospheric models like GEOS-5 will work closely together to better understand both human emissions and natural fluxes of carbon dioxide. This will help guide climate models toward more reliable predictions of future conditions across the globe.
So we put that together. That's kind of giving you a little bit of a look at where things are right now. But I want to start off by giving you guys a look at the future. And so the IPCC also produces scenarios stating that if we behave a certain way, this is what we can expect to happen. And here I've put up a map showing global temperatures under a scenario called B2. And you're going to see a whole bunch of different scenarios of different possibilities of what can happen. And those are not based on our lack of understanding of the physical processes, but these are based off of this is what's going to happen if we respond a certain way. Because while we understand the science as to what causes energy to enter and exit our atmosphere, we do not fully understand how humans are going to respond. And so in this example, we call this B2. This is middle of the road warming. This is a scenario where some actions are taken by national governments, but there's not a cohesive worldwide plan to reduce emissions. But we are reducing emissions somewhat, and we're going to see that we have warming, dramatic warming up near the poles, and only minor warming by the equator. And so we're going to see that where we live, we are going to have an impact in temperature. Not as great as up near the pole, but larger than those at the equator. And we're going to learn in the coming weeks about what will cause that imbalance of warming. So, when we get together, I want to break you guys up into groups and have you guys discuss a few things. And in order to prepare yourself for that, I want you to, right now in your notes, just jot down your thoughts about these topics, so that way when you come to class, we can get right into those discussions and not have to wait too long for you to think. The things I want you to be ready to talk about are, is there anything in the recent news that alerts you to climate change as an issue? I also want you to think about when someone asks you about global warming, or you hear about global warming, what's your first reaction? And then, is the warming of the planet consequential? Does it matter? And is there anything we can do about it? Is it too late? What would that even mean? These are just your general feelings about the topic, and we're going to talk about these when we get together in class. What's the goal? So, we have this climate change thing. The world's changing. We've got more energy on Earth. There's going to be more energy on Earth. And we have to balance that with, well, we use energy, we have a population, we consume things. And some balance between these things will find societal success. If we stop using energy and we killed everybody off in our population and nobody consumed anything, could we fix climate change? Maybe, but we wouldn't have societal success. That's not a good option. If we say, well, we need the energy, we have our population, we need to consume things, and we don't address climate change, that won't lead to societal success either. And so we need to come up with some way of reaching this while accommodating this and that. We have a clear relationship between energy use and climate change. When we use more energy, we get more climate change. And this is because buildup of carbon dioxide is directly related to the burning of fossil fuels, and the vast majority of our energy comes from burning fossil fuels. So we get the vast majority of our energy from producing carbon dioxide. We have our society set up where we have a high level of consumption and, compared to other times in the past, a high level of societal success. This is what we know. We need to figure out some way of having high societal success without having the detrimental impacts. Let's take a look. If we look at this figure, we can see that places that use more energy per capita have a higher GDP, which is one measure of societal success. So the more energy you use per capita, the more GDP you have per capita, and you can see the United States is up here. We're number one. And you might say, well, I heard that China is using the most energy or had the most emissions. Well, this is a per capita graph. So China, while it may be somewhere near us in energy use total, its per capita energy use is much lower. I'm going to ask you with your group on our first class together, which countries are the most successful at having a high GDP while having a low energy consumption. And we're going to talk about this figure a little bit. Where are we? Where do we want to be? Who's doing well? Who's not? So, kind of to wrap things up for today, what parameters do we care about when we're talking about climate change? We care about temperature. That's important. If it's hot, if it's cold, if we're above or below freezing. We care about water, precipitation, how much it rains, how much is evaporating, the humidity. We care about air composition, quality, aerosols, respiratory diseases. We care about carbon dioxide. We care about the strengths of winds. We care about how much sun we have, how much clouds we have. And really, one of the biggest places we're going to care about climate change is in the example of extreme weather. Droughts, floods, storms. This changes in extreme weather is where we're going to focus a lot of our effort in understanding climate change and looking at how to prevent things that are going to become or mitigate things that do happen. So that's it for our first day. Before you come to class, make sure that you've signed up on Google Classroom for a day that you're going to share your current event. And then take a picture of your notes from today and load them up to Google Classroom. And then come prepared, ready to discuss the things we did. There's a lot to this class. There's a lot to this problem. We're going to work together via the videos, via our in-class meetings, via our emails and phone conversations to get you to a place where you're comfortable with the material and are able to see how it can be useful to you. So thank you so much for signing up. I'm really looking forward to this opportunity together. I think we're going to have a great semester.